So we're going to move on from our review of ANOVAs and start talking about MANOVAs. So again, the multiple analysis of variance. And again, what I really want to stress is that as we're looking at ANOVAs and continuing on to MANOVAs, it's basically just layers. We're basically creating layers upon layers of statistical tests, and each layer looks more fine-tunedly at specific differences. So to start, let's just review the ANOVA itself, that when we're doing an ANOVA level, we can ask, what are we doing with the ANOVA? At the most simple level, it's either it basically is a single categorical independent variable with a single continuous dependent variable, which means we're looking for a single main effect. We can run it with only two levels, but at that point, again, just for simplicity's sake, we should just run a t-test. It's going to give us effectively the same results. And again, it can be either between or within subjects. Now, if we have a single independent variable with more than two levels, that's when the ANOVA becomes the appropriate test. And again, it can be either a between or within subjects ANOVA. And again, what we're testing for is a main effect, but again, it's a layer of the onion. At that point, it's now two layers. So we run the ANOVA for an omnibus test. Is there something going on between our IV and our DV? But if we find that there is a statistically significant F test, that omnibus test, we have to follow up with post hoc tests, usually Tukey's, which we're going to use to compare the actual differences between the multiple levels of our IV. So again, whether it's a between or within subjects design, if we have three or more levels of our IV, the omnibus ANOVA simply tells us there's a difference somewhere. It doesn't tell us what those differences are, so it's the first layer of the onion, and the second layer of the onion is the post hoc testing. If we move forward to the most simple of factorial tests, an ANOVA, where we now have multiple IVs and a DV, and again, at the most simple level, that's the 2x2 factorial ANOVA. Again, it's an ANOVA, analysis of variance, because there's only a single outcome, a DV, again, continuous, but then we have two IVs, both of which have two levels. Now we're actually testing at an omnibus level for three different effects. We're testing for the main effect of the first IV, the main effect of the second IV, and the interaction between those two IVs. And each of those, again, is an omnibus test. Now, in this case, if the omnibus test tells us there is a main effect for our first IV or a main effect for our second IV, we don't need to do post hoc tests because there's only two levels. So if there's a difference somewhere, it's a difference between those two levels. But the interaction is actually comparing the 2x2 interaction. So the interaction of two levels of an IV on the other two levels of an IV. So it's going to compare all possible combinations. Level 1 of IV1, level 1 of IV2, level 1 of IV1, level 2 of IV2, level 2 of IV2, level 2 of IV1, etc. I'm not going to keep going. I thought I could do it, but I started to get lost in my own head. But again, it basically, in a 2x2 test, we're going to have four different means, each one a unique combination of our IVs, and the mean being the outcome, the DV. So again, we're going to have to go one more layer of the onion to do a simple main effects. So again, we have the omnibus test, layer 1. We have the simple main effects test, layer 2. Now, if we have a more complex factorial design, in this case, two different IVs, but now it's 2+ levels on each. So we'll just say a 3x3 design. Now, again, we have only one DV, continuous. We're still at the ANOVA. We're still testing for two main effects and interaction. So we run the ANOVA, and that's the first layer of onion. It's going to tell us if there's a main effect in IV1, a main effect in IV2, and an interaction. But now, for each of those main effects, if they exist, we have to go another layer into a post hoc test. Since there's three or more levels, we don't know where the difference is. So now, not only do we have the omnibus test of the two main effects and the interaction, we now have a second layer, the post hoc test for each main effect, and then a final layer, the simple main effects. So adding MANOVA to the mix of all of this basically simply adds another layer to the onion. And it becomes a much more layered onion at this point, depending on how complex of a MANOVA we're running. All a MANOVA is doing is it has all of the assumptions and it has all of the uses of an ANOVA. It's now we just are adding additional dependent variables. And the MANOVA is again an omnibus test of is there any difference of any of our IVs on any of our DVs. So if the MANOVA test is significant, it is an omnibus test of any possible difference between any IV and any DV. So once we have a significant MANOVA, it lets us dig into the onion. It is the outer layer. The next layer is to check each DV systematically. And each DV may have multiple layers of the onion. So if we're running a very simple MANOVA with a single IV with 3 levels, so a between subjects 3-level IV on 2 DVs, the MANOVA is significant, we're now going to have to look for the main effects tests of IV1 on DV1 and IV1 on DV2, and if significant, run those post hoc tests. If we're running a MANOVA on that bottom layer, where we have a 3x3 design on 2 DVs, again, if the MANOVA is significant, we're going to examine all of the layers of the onion for that factorial design for DV1, the 2 main effects, post hoc tests, the interactions, the simple main effect, and then do it again for IV2, or IV1 and 2 on DV2, the second DV. Now, just like anything with ANOVAs, we can get far more complex. We can have many IVs with many layers and many DVs. Just recognize the more complex the design, the deeper into the onion you're going to have to go. And as we all know, cutting deep into an onion can result in tears. Okay, so let's talk about the multi-analysis of variance within that perspective. We're going to be talking about MANOVA and, of course, MANCOVA. MANCOVA simply, again, is adding a continuous covariate or a blocking covariate, a categorical variable usually with 2 levels. So we're going to talk about exactly what is a within subjects MANOVA, between and within. We're going to be talking about MANOVA versus MANCOVA. We're going to be talking about factorial MANOVA and MANCOVA, and of course the statistical assumptions of this particular statistical technique. So the first thing to kind of recognize is the difference between a univariate test, and again, univariate doesn't refer to the total number of variables, it simply refers to the outcome variables, the DVs. So again, an incredibly complex multiple regression with a whole bunch of predictors. If they're still just predicting one variable at the end of the day, that one DV, it's univariate. If we have an ANOVA that is a 3x3 by 5 by 7, gigantic complex ANOVA, but the outcome is still a single DV, that's univariate. And the analysis strategies, when we're looking at the univariate approach, we're really looking at, no matter how complex the IVs are, at the end of the day, we're simply looking at one DV. And if we're wanting to stay at the univariate level, there's a couple of approaches. The first one, of course, is to simply only have a single DV. We can also be in a situation where we may have multiple DVs, but logically and statistically speaking, they can be combined into a single DV. So, for example, if we have 3 outcomes of anxiety, we may actually notice that they're highly related, they're highly internally consistent, and it would maybe be better to, instead of treating them as 3 DVs and a complex MANOVA analysis, simply combine them into a total score DV. We could also test multiple DVs, but use separate ANOVAs. The problem with this, though, is that if we're doing that, we're going to increase our type 1 error rate. So again, every time we run a test, that test's estimates of how likely is that we are finding a result not due to chance are based on a probability estimate that we're only conducting one test. So we can also then, of course, do what we're talking about here, which is the multivariate answer. So we examine more than one dependent variable per test. Now, when we're doing this, it's kind of hard to visualize because most of the time, whenever we've been talking about predicting a single DV, we're kind of talking about effectively a 2-dimensional space, a bunch of predictors predicting one DV. In the case of multivariate analysis, we're effectively entering 3, 4, or 5D space, as the statistical mathematics of it is we're looking for clusters of prediction in multiple DVs. So we're actually testing the centroid of the combinations using a multivariate analysis. So our hypothesis here is that there is simply no relationship between our IVs and DVs. In other words, there's no clustering. We don't find a particular cluster of IVs predicting a particular linear trait in one DV, the next DV, or the third DV. Our alternative hypothesis is that we do find this clustering, that we do find patterns within the data between all our IVs and all our DVs. So the advantages for using MANOVA. The first advantage is that we can use it to replace the repeated measures design because it has no assumption of sporicity. If you think back to last year when we were talking in 520 about the repeated measures ANOVA, one of the things I said was that if you violated the assumptions, that there were statistical adjustments for this. However, a possible another answer was to not use a repeated measures design, but to use a MANOVA. And we're going to talk about that in more detail, because that's actually probably the better solution to this problem than using an adjustment, and we'll talk about why. The other reason for using a MANOVAs include reduction of experiment-wise type 1 error. So again, though it's a more complex test, it allows us to look for absolute differences throughout an entire set of IVs and DVs. And if the MANOVA is significant, we know for a fact that the effects we're finding are basically reliable in our probability estimate. So again, if we think there's a 5% less or 5% or less chance that we are finding the effects or the patterns that we see due to just random chance and error, we can trust that value. If we actually just ran multiple ANOVAs without running the MANOVA first, we really would be inflating the chance of type 1 error, because each one of those tests would be a unique estimate of that error that would not be accounting for the other tests. Also, in some cases, the MANOVA can actually be a more powerful design than running individual ANOVAs, because it allows us for the examination of multiple indicators of a construct, so we can actually kind of fine-tooth the examination. So what really is happening here is there's two situations when it can be a more powerful design. If I'm running 3 ANOVAs, each one of them looking at a somewhat similar indicator of a construct, maybe not super highly correlated, but similar constructs, the chances of me finding a difference in each one of those ANOVAs may be a little bit small if it's a weak relationship. But if I look at a MANOVA that is looking for those multiple indicators at the same time, they may actually cluster stronger in that larger analysis. The pattern may become more clear. Think of it this way: if there's a mild positive relationship between an IV and DV1 in a first ANOVA, and again a mild relationship in the second one, and a mild relationship in the third. So we have 3 DVs, the same IV, we run 3 ANOVAs. All 3 of those might just fall shy of statistical significance. But if I run all 3 at once, those mild relationships now are 3 mild relationships, all with one IV and all in a very similar direction. In that situation, the MANOVA may actually find that relationship as significant where individual ANOVAs would not. Also, if we have unrelated DVs, and they're actually not, I shouldn't say unrelated, but they're not measuring the same construct, they're maybe measuring dissimilar constructs. So DVs that are negatively correlated. An example of this might be conscientiousness and negative affect. Generally, those are negatively correlated. So in that case, that also may help us find it, because if we looked at them individually, we're simply looking at the strength of an IV on conscientiousness and an IV on negative affect. However, if we combine them, again, because the 2 DVs actually are negatively correlated, we may actually find the pattern easier to see in a multivariate analysis. So let's get back to that replacement of the repeated measures design reason for using a MANOVA. So we're going to start a what-if slide. We're back to the univariate zone. This is basically, think of this as a little sub-lecture that we can just plop right into that lecture from last year on repeated measures, when I simply said one of the alternatives to violating sporicity was to do a MANOVA. So within subjects multivariate, when we have one or many factors within subjects ANOVAs are compared to a multivariate analysis when comparing more than 2 levels. So basically what this is talking about is that when we're talking about using an ANOVA as a within subjects or repeated measures design, we have the assumption of sporicity. So in the example, Allison is examining the effectiveness of weight loss intervention. Everyone receives the intervention, and weight is measured on 3 occasions. So this is a within participant design, where it's the same people that are measured at time 1, they then are given an intervention, and then they're measured at time 2, and then they're measured at time 3. Now, again, as long as the assumptions aren't violated, this is the perfect example of when we'd use a within subjects ANOVA. But what we want to talk about is, what if we find out that assumption of sporicity is violated? So with the within subjects ANOVA, if we find out it's significant, it's basically telling us that there's a difference somewhere between time 1, time 2, and time 3. And again, we need to make paired comparisons to find out where that difference is. In the multivariate approach to this within subjects design, we actually look at multiple deviation scores. It's kind of like a series of paired t-tests. The multiple deviation scores are equivalent to multiple dependent variables where we compare the mean difference to 0. We also keep in mind the deviation scores will most likely be correlated. So we're expecting there to be correlation between these different times, and we're not actually looking at the difference between time 1 and time 2, time 2 and time 3, and time 1 and time 3. We're looking how each time varies from 0. So what that would actually look like is that if we were actually looking at a repeated ANOVA, we're needing to compare each individual person's changes from time 1 to time 2, time 2 to time 3, and time 1 to time 3. If we actually ran a MANOVA, what we're actually creating is different scores between time 1 and time 2, time 2 and time 3. So we're looking at the gaps, not necessarily the comparisons. Now, I know this is kind of esoteric, and a lot of times this will give us almost the exact same information. But the advantage here is that those deviant scores is that we're not having to actually have the assumption of sporicity. And when we actually talk about what happens when sporicity is violated in repeated measures ANOVA, generally speaking, the adjustments that we can do to that violation, none of them work very well. And generally speaking, we're better off simply running a MANOVA. So again, sporicity is when homogeneity of variance is in correlated data, gives us positive bias, the F-test. So the critical value of the F is too low. And this is Keating in 2006 really examined this problem. And what that really refers to is that we're actually expecting there to be somewhat a relationship between these various timed measures. We're expecting differences, but they also are measuring the same thing at different times. So we test for sporicity. Is it a problem with Malachi's test or Bartlett's test? Usually Malachi's. And again, the typical answer is that we use adjustment values. So we use epsilons. We basically adjust our degrees of freedom, and therefore we adjust our p-value that we'll accept, and therefore we're also adjusting our critical value to account for this violation of the test. And we briefly talked about the three of them last semester: Greenhouse-Geyser, Hunt-Feld, and lower bound. All of these, though, have advantages and disadvantages. None of them are a perfect solution to the problem, and many times you can find that actually they still are not giving you a very good accurate measure of, again, what we're actually interested in. How likely is it that we're finding this effect due to chance and not a meaningful effect? So a lot of research has gone into this, and we found that generally speaking, when you violate sporicity, your best answer is to just simply ditch the within subjects ANOVA, treat the individual measurements as unique times, unique DVs, and run a MANOVA, a multiple analysis of variance, which doesn't have that assumption of sporicity. If you find the effect that you're expecting, then you move forward with your post hoc test and find out where the difference is. So that pretty much ends our little side lecture back to univariate land of one of the reasons we would use MANOVA is simply when we're wanting to do a within subjects ANOVA, but find that we violated assumptions of variance, specifically sporicity. In that case, we would simply enter that same data into a MANOVA, basically a between subjects ANOVA, even though it's not between subjects, treating each time measurement as a separate DV.